Why would you want to trip a hypersonic flow boundary layer? That is a good question, and a goal that many hypersonic researchers have investigated. Now, just a quick background on what hypersonic flow is so we can better understand the context. So hypersonic flow is when the flow is traveling, as a general rule, above Mach 5, so 5 times the speed of sound. It might seem odd that there is this phase called hypersonic flow. I mean, we have subsonic flow, which we understand very well, and we know that it's when the flow is below Mach 1, so below the speed of sound. Then we have supersonic flow, which again, we naturally understand to be greater than the speed of sound, and that makes sense. But now we have hypersonic flow. What's up with that? Well, a hypersonic flow is when the chemistry of the fluid that you're in this case air, changes. In particular, the various components of air start to ionize. So the electrons in their outer shells start to rip off, and now you have all sorts of different forces that are important. So for example, we have thermodynamically induced forces and electromagnetic forces because of the ionized atoms. Along with that, there is a lot of heating. So that is why we need to have this distinction between supersonic and hypersonic flows, and why it is so important to have this distinction. So bringing this back to tripping a boundary layer in hypersonic flow, why would we want to do that? Well, it comes down to what we can use hypersonic flows for. So in this podcast, we're looking at a scramjet in particular, which are arguably the coolest type of jet engine. And just to give a quick explanation as to what scramjets are, let's talk about regular jet engines first. So a jet engine is one where you take air in through the inlet, then you compress it, then you dump fuel in it in the combustor stage, then you burn it, then sometimes you extract energy through a turbine to then run the upstream compressor, and then you throw the flow out the back at very high speeds to generate thrust. And the way it produces thrust is very Newtonian, where every force has an equal and opposite reaction. In this particular case, the act of throwing flow out of the back means there is a force pushing in the opposite direction on the jet and whatever the jet is connected to, and that pushes the jet forwards. That is why a jet engine that is what it is in a nutshell. And from here, you can then decompose the general idea of a jet engine into many different types. So in terms of a scramjet, it is amazing because it doesn't necessarily have any moving parts. Literally from its geometry, the various functions of the jet engine can take place. So to begin with, the air enters the inlet, and if you reduce the cross-sectional area of the inlet, simply through making the geometry more constrictive, the air gets rammed into the inlet, and that dramatically increases the pressure. So right there, you have the compression phase of your jet engine done. You don't need a compressor, or you don't need any other turbo machinery to compress the air. You're good. Then, in a similar fashion to the other jet engines, you then direct the air into the combustor, you add the fuel and you burn it, and that provides the massive increase in energy in the flow, and that is what you'll use to end up producing thrust. Now, after the combustor, you don't really need a turbine because you don't have any of this compressor stage. They don't have a compressor upstream. They need to power with energy from the flow. So now all you need to do really is to expand the air through the nozzle and then throw it out the back to produce thrust. As such, a scramjet, because it has fewer sections and the possibility of no moving parts, it is much simpler than a turbojet, for example. But there is another major advantage to it, and that is for a scramjet, the flow through the engine stays supersonic. Because the air is supersonic, it is moving really fast, and that means you can get a faster velocity out of the nozzle, which means you get more thrust. So scramjets have the natural advantage of producing more thrust. But there are a few major weaknesses too. The first one is that the combustion stage is incredibly sensitive, and for a few reasons. First, for example, the faster you travel, the more air you'll need to get into your inlet that you'll get there, and that means you need to have a very fast response and accurate way of controlling how much fuel to dump in. What's more, you need certain pressures in order to operate. If you have no moving parts, you can't really control the pressure that the combustor sees. As such, often scramjets, even though they may not need a moving part to operate, they will actually feature a cone in the middle of the inlet that you can push forward or backwards, and doing so either blocks the inlet more or less, which then changes the pressure and the compressed air. That means that you can have variable conditions. Another major difficulty with the combustor is trying to ignite the fuel, and this is actually really cool. So this is because fuel is very sensitive to its conditions. So for example, did you know that you can actually cool a fire so much that it will extinguish? In addition to that, you can also strain the fire so much, so literally pulling it apart, so that the surrounding unburnt fuel can't catch fire. That then extinguishes the fire. And that is the exact problem scramjets have. Because the flow is so fast, it's supersonic, the fire gets strained and it is really hard to then sustain the burn, even if you have enough fuel in the system. That then leads to the engine going out. That then leads to another major problem, which is trying to restart it. So scramjets are notoriously hard to get started, and that is because they require very fast flow. And the flow needs to be entering the inlet in a precise manner, otherwise there will be separation, not enough pressure, or even not enough flow. So from this brief description of these potential problems, hopefully it is clear how delicate the operation of a scramjet is. Yes, it has major advantages, and in hypersonic flows it is really the only type of jet engine that can operate. But that comes at a cost of needing very precise designs. And that brings us to today's podcast, tripping the boundary layer of a flow entering a scramjet, which is hypersonic flow to begin with. From the scramjet description above, we can now understand that the flow entering the scramjet is incredibly important, and that's really the case for all jet engines, but even more so, you could argue, for scramjets. And that's why we would potentially want to trip the boundary layer here, and that is to reduce the flow's tendency to separate in the engine or just upstream of it. If the flow did separate, that would make the scramjet almost impossible to design well. I mean, the variability in the flow conditions would be so difficult to accommodate. As such, tripping the flow in the boundary layer here to turbulent as it enters the scramjet provides a scramjet with much more uniform flow and higher pressures to work with, which also increases the efficiency. And tripping the boundary layer is more important for small scramjets because obviously there is a lower Reynolds number, and the chances of the boundary layer naturally transitioning to turbulence is much lower. Now, while tripping the boundary layer offers this massive benefit, it also comes with a potential problem that is changing the heating rate, which means you need to account for the different heating rates brought about through the different boundary layers, so you can add enough thermal protection to the jet so it doesn't melt. Oh yeah, I should also mention that in hypersonic flows, there is crazy heating, and that if there isn't enough thermal protection, that will lead to structural failure. And there is one more really interesting thing that this heating and its interaction with the thermal protection does. So probably the most common type of thermal protection for hypersonics vehicle is something called ablative heat shielding. That is literally when you have a material on the surface, often ceramic tiles, that absorb heat and burn away, the ablative part of it. These tiles are not there to take any of the structural loading, but simply to protect the structure that is taking the loading from the heat. Now, these tiles work incredibly well. That's what the space shuttle uses, for example. But as they burn away, the surface roughness changes, and that changes the heating pattern, and slight gaps in the tiles can lead to non-uniform roughness and concentrated heating, which leads to faster ablation of the tiles in this area and potentially failure as the heat enters the underlying structure and makes it weaker. And one aim of this study was to determine the dimensions of the boundary layer trips required to promote in a controlled and predictable manner, as the researchers say. So this topic is fascinating in all the little nuances you have to consider. So in figure 3, we see one type of device the authors considered for tripping the boundary layer. If I scroll down here we go. And it's somewhat surprisingly that they are vortex generators. So these are vortex generators here. As the flow comes along, it spirals up into counter-rotating vortices. And that is a little bit surprising, not in the vortex generators were used to delay stall, but that they were also used for tripping the boundary layer. That makes sense that the vortices coming off of these things can trip the boundary layer, but usually their function isn't described as such. So it's interesting to see it from that point of view. Now, the researchers tested a bunch of different devices, as we'll see later, and some were passive, which offers a simple solution, while others were active, which offers a way of tailoring how much tripping is going on, so you get enough for the situation you're in. They tested these devices on the HyperX forebody, and the HyperX was an unmanned hypersonic aircraft, as you see in this right figure here, by NASA, and it reached up to Mach 9.3. That's insane. And it has a scramjet. And the way they launched the aircraft was by attaching it to a rocket and then dropping it from a plane. The rocket would then fire, getting the HyperX up to speed. Then the HyperX would then detach from the scramjet, and then the scramjet would start from there and power the HyperX vehicle along its way. This stunning method illustrates another peculiarity of scramjets, in that you need to be traveling really fast before they can even start. At slower speeds, you don't get enough pressure at the inlet from the air ramming in because the flow is not fast enough, and hence in the combustor you won't be able to burn fuel properly and the engine just won't start. Anyway, coming back to the boundary layers for the HyperX. So the boundary layer transition was not predicted to occur for a regular HyperX vehicle. So there was a very real possibility of shocks inducing separation. So as the flow comes over the HyperX vehicle, it goes over this shovel nose as they call it, and then a shock will form and that will make the boundary layer separate. that then results in very chaotic flow entering the inlet, and that's not what you want. You want to have much cleaner flow. And for the HyperX here, the front of it, as shown in figure 1, compresses the incoming flow through the ramp and it directs it into the engine. And there are 3 main ramps before the inlet. Now in figure 6, we see the different configurations for the blowing boundary layer trips that these researchers considered. So as I mentioned, they did passive and active. The active ones are these blowing boundary layer trips. They range from various holes placed systematically around to slots to zigzags and straight slots as well. So the idea behind these holes and slots is that apparently by blowing air into the system, these trips act very similar to passive spheres on a surface. So instead of having actual physical roughness, by injecting quite high pressure air into the system from these holes, that can trip the boundary layer. And in figure 4 in the bottom right here, as we scroll up just here, let's zoom in a little bit, we see the physics of how this blowing affects the boundary layer, and in effect, several shocks form around it. So we have the flow coming out here being jettisoned into the flow, into the boundary layer, and it trips the boundary layer. Now, the testing facilities for this research were awesome. They had 2 wind tunnels, a 20-inch Mach 6 wind tunnel, and a 31-inch Mach 10 wind tunnel. So the 20 inches and 31 inches may not seem like a lot, both are less than 1 meter, but to be able to generate Mach 6 and Mach 10 flows, it is very impressive for such a big wind tunnel, and they can apparently run these wind tunnels for up to 15 minutes at a time at Mach 10. That's insane. That's incredibly hard to do, and if you go to the vast majority of hypersonic wind tunnels around the world, they can operate only for a few seconds, like not even 1 minute, like 10 seconds is normal, not 15 minutes. And while they can do 15 minutes here, apparently they only need like 5 seconds or so to get the data that they need. That's why a lot of other hypersonic wind tunnels only operate for seconds and not minutes. So the stagnation temperature of these flows is over 500 degrees Celsius, which is enough to cook a hot dog. And to visualize the boundary layer over the HyperX surface, they used these tiles that were coated with a phosphor and in 2 different fluorescent colors, red and green. And based on the intensity of the glows through calibrations, you can then tell the surface temperature distribution. In addition to this, they also used Schlieren, which is a great way to visualize shocks and really anything that causes changes in density of the air by quite an amount. So like even a flame, you can use Schlieren to visualize the heat waves coming from a flame kind of thing. They also used oil flow, which is where you mix oil with some kind of fine particle so you can see where the flow is going. You can then see as the flow goes along where shocks are occurring based on discontinuities on where the particles are congregating. Now in figure 7, we can see the diagrams of the HyperX, and one thing to note, if I scroll down here, this is the HyperX. One thing to note here is that only the forebody was used in this research, and that's because of the geometric limitations of the wind tunnel. As I mentioned, it's only a 31-inch cross-section wind tunnel. That's still really good, but it's still quite small for a massive plane. So they needed to scale down this HyperX to 1/3 scale and just use the forebody. And you can see still it's 28 inches long. In the top image, you can see the leading edge that then leads to the wedge on the aircraft that then leads to the inlet, and you can see the different ramp sections. In table 2, if we scroll to that one up here, I think it's up here. No, down, like sorry. So in table 2, we see the test conditions, and it's awesome because, yeah, they use all these units that render the information, essentially hieroglyphs, so that's pretty great. But anyway, overall, there isn't too much really to be concerned about here, really only that the Reynolds number, which is 2.2 million per foot, and if I'm reading that correctly, which results in a 28-inch length of the HyperX forebody, so this 28-inch here, means that the Reynolds number of that is about 5 million. And the reason why this is interesting is because you might be thinking that that's really low considering how fast this flow is. I mean, even at Mach 10 that they're looking at, the Reynolds number is just over 5 million. But that is because the characteristics of the air have changed so much that the Reynolds number is surprisingly very low. The same thing happens when you go to supersonic flows and even when you fly at very high altitudes. The air gets very thin and the Reynolds number drops a lot. Now, let's move on to the results. In figure 9, we see some really cool results. Let me zoom in here because there's some interesting things to see. So this is the forward body of the HyperX at Mach 6 in the left and Mach 10 in the right columns respectively. The authors wanted to compare the results to make sure the wind tunnels, the Mach 6 and Mach 10 wind tunnels, gave the same results. In the bottom two figures, we see the results of the oil film. And from these figures, the authors concluded that the boundary layer was laminar because you can see these lines going like vertically along. That is the corners of the ramp, so the different ramp sections on the underside of the HyperX, which is compressing the flow. And these lines show flow separation because if we zoom in, for example, just here, and by the way, these pictures are really high quality, like awesome quality. Anyway, after each line, we see non-uniform flow, and that is separated flow. So it's indicating that potentially there are shocks forming that are then causing the boundary layer, this laminar boundary layer, to separate. So it is good that both of these wind tunnels are showing pretty much the same results. And just quickly, the researchers in figure 10 give some results of a couple of passive trips from other works, and shown here with this fluorescent FlowVis technique. Now, they don't give too much information about these trips, particularly their geometry, but I just wanted to go through these results because one thing they show is that increasing the height of these two different passive trips, trip 1 and trip 2C, whatever they are, they're in different research papers. The bigger the trip is, the more the effective it is at tripping the boundary layer. And so it's nice to see that that trend also holds here at Mach 10 flows as it does at supersonic and subsonic flows too. That is the case. When you have a bigger trip, generally it will trip the boundary layer more effectively. The tripping will happen further upstream, as you can see here by the yellow and green lines migrating further upstream. Let's now move on to the active boundary layer trips, what they really looked at in this paper. So in figure 11, if we scroll down here, so we see the effects of configuration H5, which from figure 6, if we scroll up, is just a single row of holes, as we can see here. So H5 here is a single row of holes, 17 along. Each hole has a diameter of 0.2 inches and a spacing of, 0.02 inches and a spacing of 0.125 inches. And then air comes out of here at different pressures. The left column of images in figure 11 is the Schlieren results. So the white lines are the shocks. If I zoom in, these white lines here are the shocks forming. And the right column is the fluorescent data. To begin with, in the top row, there is no blowing, so the pressure coming out of the holes is the same as the surface static pressure. And the transition perhaps occurs past the third ramp. So we have ramp 1, 2, 3, then the inlet, and perhaps in the inlet region, perhaps, maybe not. It's a little bit qualitative at the moment. And as the pressure of the blowing increases, as given by the P on P2 ratio here, we can see that the blowers are successful in making the boundary layer transition further upstream as given by the green to yellow region. So as the pressure increases from nothing to 5 times the surface static pressure up to 250 times the surface static pressure, this green-yellow region migrates very far upstream. And interestingly, it isn't until the pressure coming out of the holes is 20 times the surface static pressure that we see a significant change in the transition location. So there's like kind of a massive jump here between 5 and 20. Now in the Schlieren, we can see that there is a shock forming at the blower whenever the blower occurs. So there's no blower here, there's no shock around here. As soon as the blower occurs, we get another shock forming here. And in fact, the authors have labeled the shock induced by blowing for the middle row, that's when P on P2 is 20, but even for the second row, when there is a little bit of blowing, there is, but at a much lower pressure, there is still a faint shock occurring just here if you look closely. It's not very strong, but it is there. So it is always surprising just how easy it is to create a shock at supersonic and hypersonic speeds. Literally minor disturbances and you got a shock. So these images are great, but they also wanted a more quantitative way of seeing where transition occurs. So in figure 12, if we zoom in here we go. They show the average heating distribution over the surface to see where the heating dramatically changes, which would then correspond to transition. The black circles here, encompassed by the green, are for no blowing, and the green is actually for a 10% error bar, or uncertainty, more like it. Now, one thing that is interesting is that at the start of each new ramp, because the underside is made up of 3 ramps, effectively, where they're connected, it is a discrete jump in the angle that it is compared to the actual aircraft. But when a new ramp starts, the heating jumps up suddenly. So it goes fairly constant, jumps up, then goes fairly constant, jumps up, fairly constant, and so on. Anyway, we can see that for the blue circles just here, which corresponds to the lowest blowing pressure configuration, 5, relative to the static surface pressure, the heating slightly increases from about the end of the third ramp, so about just here. That indicates perhaps some earlier transition from these blowers, but not by much compared to no blowing. Then as the blowing pressure increases more and more, the transition occurs more and more upstream. You can see it just migrates further and further upstream. So when the pressure is 20 times greater than the surface pressure, transition occurs at the first ramp. So this is quantitative proof that the blowing is highly effective at transitioning the boundary layer. Let's now move to figure 17 because the authors show the shock systems created by some passive flow control devices and for the different blowing devices as well. So figure 17 is just here. And in the left column, we have a simple step in the top figure and then a vortex generator in the bottom one. In the right column, we have H4 in the top right and S2 for the bottom right, which from figure 6, if we go back to here, just quickly, I want to show you what they are, H4 and S2. In figure 6, we see H4 is 3 lines of these holes, 3 rows, and S2 is a zigzag slot. So going back to figure 17 to see what the results are on the with the Schlieren results. Here we go, zooming in. So overall, the shock systems for the blowers are pretty much identical. The only real difference is perhaps the third shock that is present for the S2 down here, the third shock downstream, as opposed to for the H4. It maybe is there a little bit, but it's quite weak. But other than that, the shocks are pretty much identical. On the other hand, the passive flow trips are quite different in terms of their shock systems that they're producing. The step has 2 shocks, one from the separation, from the boundary layer separating from the shock, and then one from the leading edge of the shock, which then intersects because they're at different angles coming off. On the other hand, the vortex generator doesn't seem to have the separation shock. Maybe a little bit of one, but not too much perhaps. Another interesting difference is that the blowers only penetrate up to half the boundary layer, while the passive trips penetrate the entire boundary layer. So the author suggests that as an approximation, the blowers then need to penetrate twice the height of what these ones are currently doing in order to be able to compare them to the passive trips. So perhaps twice the pressure or whatever that is. And with that, we come to the end of this podcast. I learned a lot from this paper. One good thing is that for hypersonic flows, trips work pretty much the same way as they do with subsonic flows as well. So that's something really nice because often you never know if a device will work the same way in sonic speeds and supersonic speeds as it will in subsonic speeds. So that's good to know. So if you like this episode, hit the like and subscribe button. And if you want to learn OpenFOAM, which is a very powerful and free software, but it's very hard to learn, take our course and link below. We go through everything from basics all the way to very advanced meshing like dynamic and overset meshes, which aren't really covered very well anywhere. And we have some really good feedback on there. And if you are doing experiments, did you know that you probably have a 2 to 4% error in your data and you don't even know about it? It is because of the changing conditions in the atmosphere. And in the MC Hawk link below, you can find the math behind it as well as how to fix that problem. And with that, we'll see you next one. Peace out, amigos.